Go into the next topic with respective to the second module, which is pertaining with scaling and small geometry effects and along with MOSFET capacitances. So the purpose of this particular topic is we need to shrink the size of the IC. When you're shrinking the size, you have to have a different dimension. So the dimension exists as it is, but you have to scale it. You have to have a parameter which has to be scaled. Normally we write the scale on the graph. So 1 centimeter is equal to 10 volts or 1 centimeter is equal to 1 meter. But that doesn't represent that it is 1 meter. Then when you go back and scale up, you do the reverse procedure. If you have 5 blocks on your graph, it is nothing but 5 meters, because one block represents 1 meter. So this is how the scaling helps us, and we are all quite familiar by now, I hope. So we'll look into this topic now. Alright, we look into the next topic, which helps us to find out the delay in a logic gate. So how exactly is the delay considered? You have to consider the delay because of the RC, parasitic, so many other parameters which we have already discussed. So now we will consider this problem. Use the linear delay model to estimate the delay of a fan out of 4 inverter. That means inverter is driving 4 devices at the output side. Assume the inverter is constructed in a 65 nanometer process with the propagation delay tau is equal to 3 picoseconds. So we need to find out the linear delay or the delay in a logic gate. And the gate is nothing but a simple inverter, which is one inverter forcing or driving 4 more inverters. So we all know that the logic effort of the inverter is G, which is equal to 1. We have just now found out a normal and or a unit inverter is of size 2:1, and therefore combining this, the input capacitance is 3 and the output inverter capacitance together, which is nothing but the drain or the diffusion capacitance, is 3. 3 by 3 will give you 1. Therefore the logic effort of an inverter is nothing but G, which is equal to 1. Now, what exactly we are supposed to do here before calculating the delay is find out the electrical effort. So what is the electrical effort? As in other words, I have already told you, H is, as per the author, H is nothing but called also as electrical effort. So what is H? H is nothing but the fan out. So how much devices it is driving? 4. 4 devices your single inverter is driving, therefore fan out is 4, and in other words the electrical effort is also 4. So the electrical effort is 4 because the load is 4 gates of equal size. It is driving a load as 4 devices. Therefore logical effort is 1, electrical effort is 4. Next, parasitic delay. Just now we have seen what is parasitic delay. It is nothing but the diffusion capacitances into R and C. What is the diffusion capacitance of the inverter with the ratio 2:1? 2 plus 1 diffusion capacitance will give you 3. Therefore, the parasitic delay of an inverter is 3 RC. But if you take it as P inverter, parasitic delay of an inverter is given to be 1. Therefore, the total delay is calculated as this formula GH plus 1. So, G is 1, H is 4 and the P parasitic delay is found out to be 1. Therefore, 5 in normalized terms. But P inverter is 3, right? Therefore, 5 into 3 TPD is 15 picoseconds in absolute terms. So the delay is given as P inverter is assumed to be 1, but together it is 3 RC. So in that case it gives you 3, and when you multiply it with this value, it is 15 picoseconds in absolute terms. So this is the delay in a logic gate. So often path delays are expressed in terms of FO4 inverter gates. Normally path delays are considered only with 4 output load inverter with that delays. While not all designers are familiar with the tau notation, most experienced designers do know the delay of a fan out of a 4 inverter in the process in which they are working. Yes, most of them will not know, but still people should be aware. And just now we are itself telling what is the meaning of tau and what is the delay of a fan out. So tau can be estimated as 0.2 FO4 inverter delay, fan out of 4 inverter delays. So even if the ratio of the diffusion capacitance to gate capacitance changes, P inverter will always be 0.8 or 1.2 rather than 1. So slightly it varies from 4.8 to 5.2. Therefore, the delay of a gate dominated logic block expressed in terms of FO4 inverters remains relatively constant from one process to another, even if the diffusion capacitances, that means the delay of a gate dominated logic block, always this is where we call it as gate dominated, means the input is given at the gate in terms of FO4 inverters will always have a relative constant from one process to another, even if the diffusion capacitances don't. So it always normally remains to be a constant. Next topic is something called as drive. So what is drive? The sizes are typically labeled with their drive. Whatever is the size is dependent on driving capability. Drive how much? So for example, a unit inverter may be called as inverter 1x. An inverter of 8 times unit size is inverter 8x. So a 2 input NAND that delivers the same current as the inverter is called as NAND 2 undercross 1x. So it is often more intuitive to characterize gates by their drive X rather than their input capacitances. So how many inverters? 8 times unit size it is supporting, then it will call it as 8. So if we redefine an unit inverter to have 1 unit of capacitance, then the drive is given by X is equal to C in by G. So G here is the gate, and in terms of delay, in terms of drive, the delay is expressed as C out by X, output capacitance by X, where X is the drive, plus P. P is your parasitic capacitance. So this is one more formula which is helping us to calculate the delay using drive. Drive here is noted as X. So X is nothing but the input capacitance. So it is defined here as the input capacitance divided by gate. Now we go on to the next topic, which is logical effort of paths. So before going into what is all about logical effort, designers often need to choose the fastest circuit topology and gate sizes for a particular logic function and to estimate the delay of the design. Dear all, most of the exercises are not considered because of lack of time. If that is also considered, I think you would have had a more better approach. So please refer to the textbooks for the examples problems. Maybe later on we can consider those examples which can be added. Designers need to choose the fastest circuit topology because speed is a parameter which is to be considered here. So you have to design a circuit or the diagram which is having fastest speed, or the propagation delay should be less, and also gate sizes for a particular logic also should be considered to estimate the delay. So not only the circuit design, the gate size also to be considered. So therefore simulation or timing analysis gives very poor results. They are simple tools and they only determine how fast it is. They will not tell where the problem is, how to rectify or how to modify. So tools just help us to tell what is the speed, how it will operate, and whether the implementation can be modified for better results. That and all such things are not found out in the simulation tool. So an inexperienced designer often end up in minor changes. Sometimes if you are not experienced, you are not aware where exactly the need of the change to be done, then you don't get the better speed. So then we call that person as inexperienced designer. Therefore, to aid the help of such kind of people, we have something called as logical effort. So what exactly logical effort means? It helps us to provide a simple method on the back of an envelope to choose the best topology and the number of stages of logic for a function. So the purpose of logic effort of paths is to choose the best of the best circuit design topology, and also tells us how many number of stages of logic should be considered. Because as the number of stages increases, the delay also is taking more time, speed is reduced. Therefore, that is calculated with the help of something called as logical effort. So based on the linear delay model, it allows the designer the best number of stages for a path, the minimum possible delay and gate sizes. So based on the linear delay model, it allows the designer the best number of stages. Yes, based on this you get the best number of stages for the path and minimum possible delay, and also gate sizes are also redefined. So the techniques of logical effort will be revisited throughout this text to understand the delay of many types of circuits. So I hope you have understood the meaning of logical effort. It helps us to have the better size of the transistor. It helps us to have lesser delay. It also helps us to have lesser or fewer number of stages. So with the help of this, we are able to calculate logical effort. So far we have understood what is logical path. Now we will try to find out what is the delay in a multi-stage logical network. So multi-stage is you have many circuits ahead. One is driving the other one, and the other one is driving the other one. Like this, it has a cascaded structure which is called as multi-stage. So figure shows the logical and electrical efforts of each stage in a multi-stage path as a function of the sizes of each stage. Alright, we have the first device, which is the gate. So gate input is 1, and the propagation delay, 1 second, the value is given here as 10. So G is nothing but G is one, which is based on the size of this inverter 3 by 3. So G is 1, and H is fan out, which is given by X by 10, since the number is given here. That means it is driving a device as X. How many fan out, how many device it is driving, and the value of H. Next is your NOR gate. For NOR gate, it is 5 by 3, and H2 is which device it is driving, Y, and what is the value inside, that is X. Similarly G3, this is your NAND gate. For NAND gate it is 4 by 3, and H3 is the fan out. It is driving a device of size Z and divided by Y. G4, again this is an inverter, therefore it is 1. H4 is, it is driving a load of 20 divided by Z. So the path of interest is marked with a dashed blue line. This is how we have to come with. Observe that logical effort is independent of size, while electrical effort depends on the size. So what is it? You have logical effort. So the logical effort is G, which is independent of size, because it is based only on the input capacitance and the inverter capacitance. Whereas electrical effort, which is fan out, it is dependent on the size. So path logical effort, what is the logical effort in the entire path is given as G, capital G, is the product of the logical efforts of each stage along the path, Gi. So the product of all G's is the path logical effort. So in our previous example, multiply all the G values, that gives you capital G, which is called as path logical effort. Similarly, path electrical effort, which is fan out, and that is given as capital H. Fan out was given as lowercase h, now it is capital H. This is the ratio of the output capacitance the path must drive divided by the input capacitance represented by the path. So in the entire path, it's the ratio of the output capacitance the path must drive. So whatever is the capacitance in that entire path, that is output which is driving, and the input capacitance present by the path will be considered here. So C out by C in will give you capital H, which is path electrical effort. Next we have path effort capital F. So effort is given by C into H. So capital F is the product of the stage efforts of each stage. For one stage you have GH, second stage you have another GH. The product of those two will give you path effort F. Recall that the stage effort of a single stage is F is equal to GH. So in paths that branch and F is not equal to GH. So sometimes you have a straight path, but here there is a path which is branching. Then in that case F is not equal to GH because it has two-way branch. Then how to calculate? Therefore, consider a path from the primary input to one of the inputs. Consider any one path, either come down or go up. So the logical effort G is given as 1 into 1 inverter, and the capital H is given by output 90 and the input capacitance 5, 90 by 5, which is equal to 18. Therefore GH is equal to 18. But capital F is nothing but F1, F2. Therefore you have to multiply both. So it turns out to be 1 into G is 1, H1. H1 is 90 by 15, 6 and 90. 90 by 15, which is 6, 1 into 6 will give you 36. So even though you have two branches, each one will contribute 18 and together they contribute 36, 18 plus 8. So in other words, F is equal to 2GH in this path on account of two-way branching. So whenever you have two-way branching, it can be calculated like this. Just now we have seen how the effort has to be calculated for branching. So therefore we now have a topic related to that, which is defined here. So therefore we must introduce a new kind of effort to account for branching between stages of a path. So crudely it was calculated, but now we will have a logical statement which tells how the branching effort, which is indicated as B, calculated. So the branching effort is the ratio of the total capacitance seen by a stage to the capacitance on the path. So whatever the capacitance you see on the path, of the path, that is nothing but the total capacitance divided by the ratio of on the capacitance which is existing. So according to us, on path and off path, it is 15 plus 15, and on path is 15, therefore it gives you 2. So the path branching effort B is the product of the branching efforts between two stages, and this is how the branching effort is calculated. Now we define the path effort F. So path effort F is defined as the product of logical, electrical and branching efforts. So logical is given by G, electrical is given by H, and branching efforts is B. So all these things are considered, and that gives you the value of F. All parameters included has to be multiplied. And then we can now calculate or compute the delay for a multi-stage network. So the multi-stage network is given by, the calculation of the delay is given by D, which is the summation of Di, where Di is Df plus P. So the path D is the sum of the delays of each stage. It can be written as the sum of path effort delay and the parasitic delay, which is P. So where df is nothing but summation of fi with respective to the inputs, and p is also the parasitic capacitance associated with it. So using all these things, combinations will give you the entire delay in the different stage or multi-stage network. So the product of the stage efforts is F. So path effort delay is the sum of the stage efforts. Just now we had a discussion. The sum of the set of numbers whose product is constant is minimized by choosing all the numbers to be equal. Therefore, in other words, the path delay is minimized when each stage bears the same effort. Okay, now we have to calculate the stages. So, if a path has n stages and each bears the same effort, the effort is calculated using the formula as F is equal to GIHI, which in turn is given as capital F of 1 by n. Thus, the minimum possible delay of an n-stage path with path effort f and parasitic, when you substitute, the f value is replaced by f to the power of 1 by n, and n is the n stage. So, entire delay is calculated as n into f 1 by n plus n. So, this is the logical effort result, and which it shows the minimum delay of the path can be estimated knowing only the number of stages, path effort and parasitic delay. So conclusion, the delay can be calculated by knowing how much number of stages are there, what is the path effort and what is the parasitic delay. So this is superior to simulation. In simulation, the entire information or where exactly which stage or which path effort or which logical path was having problem, that was not identified, but in this way or in this procedure, therefore it is possible, and therefore it is superior to simulation, in which the delay depends on sizes and you never achieve certainty that the sizes selected are those of they offer minimum delay. So this is how delay can be reduced, and by having better design, and that design is in turn related to path effort or the number of stages or the parasitic delay. It is also straightforward to select gate sizes to achieve this least delay. So the gate sizes also can be achieved. Gate size is nothing but your ratios width that can be controlled. So the capacitance transformation formula to find the best input capacitance for a gate given the output capacitance it drives is got by combining two equations. So F is equal to G into H, where H is C out by C in. Now how to select how many stages has to be considered. So given a specific circuit, we now know how to estimate the delay and choose the gate sizes. But now we have to understand how many stages has to be considered. So logic effort tells us that NANDs are better than NORs, and that gates with few inputs are better than gates which are having many inputs. So we will use logical effort to predict the best number of stages. So logical effort helps us to tell how many stages are going to be used. So the designers sometimes estimate delay by counting the number of stages of logic, assuming each stage has a constant gate delay. So each stage will normally have a constant gate delay. This is how the logic designers think. So if you have a stage of 2 seconds delay, and if there are 10 such stages, it gives as 10 into 2 20 seconds of delay. So crudely this can be calculated, but this is potentially misleading because it implies that the fastest circuit are those that use the fewest stages of logic. So somewhere one circuit may have lesser logic, lesser gates. So in that way you can't every time come to the conclusion that it is the product of the gate delay and the number of stages. So accuracy is what we look now, because we have achieved one kind of saturation, we need to be the best. Therefore, the gate delay actually depends, all of us know that it depends on the electrical effort, and therefore electrical effort is nothing but your fan out. Therefore, fewer stages should be completely responsible for delay. So sometimes fewer stages also results in more delay, because there may be 2-3 stages, but each stage is having a complex circuit, and that can also result in more delay. So based on all these challenges, we need to calculate how many stages or what is the best number of stages we need to have. So accordingly, lesser the number of stages, better is the circuit, but still how to go along. So looking into all these considerations, we go ahead. So in general, inverters can be added to the end of a path without changing its function. So when you look here, normally inverters are added in the end without changing any path. Now compute how many should be added for least delay. So calculate what is the least delay. The logical block shown below has n1 stages and a path effort of f. So consider adding n minus n1 inverters to the end to bring the path to n stages. So you have to reduce the value of n. Extra inverters do not change the logical path effort but to add the parasitic delay. So the delay of the new path is calculated by this formula. The scope of explanation is beyond, and therefore we simply assume the final formula which gives the delay of the new path, which is dependent on n value, as n f raised to the power of 1 by n plus summation where I is equal to 1 to n1 pi plus n minus n1 into the propagation delay of the inverter p inverter. And differentiating with respective to n and setting to 0, we find the final expression. The result can be expressed more compactly by, this is what is the differentiation done, and this in turn gives you p inverter plus rho into 1 minus ln of rho, where ln value of rho value is 3.59. So substitutions and all such things which help us to tell us what is the n value. So the summary of this logical effort is, the path effort is calculated using the formula F is equal to GBH, and the best number of stages is calculated as n is equal to log 4 of F. Sketch the path, and the delay is calculated using the formula n into F raised to power 1 by n plus P. The best stage effort is calculated using the formula lowercase f is equal to capital F, multiple stages, right? Starting at the end, work backward to find the sizes. Find the inverter input size, which is calculated by total capacitance into the effort, logical effort divided by fan out. So this is the formula which is having the expression. So substitute the necessary formulas in order to calculate if any problems are indicated. And as I told you, please also refer to the examples given in the textbook.